Good morning, everyone. I have the honor to introduce our speaker, Dr. Andrew Knight, who's an Associate Professor of Organizational Behavior in the Olin Business School at Washington University in St. Louis. He studies the interpersonal dynamics of groups and teams with a focus on affect and relationships within healthcare and entrepreneurship. As Sonia mentioned, he will be describing his article using recurrence analysis to examine group dynamics, and we look forward to hearing his presentation today. Thank you so much, Dr. Knight, for being with us.
Thank you very much. I am excited to participate in this webinar, and I will also keep my eye on the question box, and please feel free to submit questions as we're going along, and I can try to address things as your questions come up and we're going forward. Let me give just a broad overview of where we're going to head in this webinar. I want to take a little bit of time at the outset just to explain the rationale behind and some uses of recurrence analysis for those who may be less familiar with the technique. And then I want to give a conceptual overview of how to do a recurrence analysis. And so in that, I'm going to stay at a relatively high level and not really get into the weeds, just trying to communicate what's going on when you're doing a recurrence analysis. Then I'm going to walk step by step through how to use recurrence analysis. And I'm going to do this using some data on activation in groups that are facing a deadline. And as I'm going through this, I'm going to do this actually using code and R, walking through the different components and highlighting some of the key decision points that you have to make when you are doing recurrence analysis. And for this, I will be using the CRQA package that is in R. There are some other options, and I'll describe some of those other options for you as we go forward. Then I'll wrap just by highlighting a couple of extensions of recurrence analysis. What I'll be showing today is a basic initial version of recurrence analysis, but there are lots of extensions of this technique and different ways of applying this, and so I'll discuss a couple of those, and then also provide some pointers for more information. Obviously, in a 45-minute or so session, we don't have quite the time needed to go into depth that's needed on this pretty nuanced and complicated technique, and so I'll give some pointers for some useful resources that might be helpful. Let me start just by describing a bit of my perspectives and how I came to learn about recurrence analysis. In general, as Nora mentioned, I study issues of groups and teams and relationships in the workplace. And so some of the questions that I tackle are things like, why do some people gel while other people clash in the workplace? Why do some people have more influence than others in the workplace? Kind of at a higher level of analysis, why is it that some teams are terrific and function very effectively and get great things done, whereas other teams are ghastly and tend to blow up before they do anything that's constructive? And so I came to become interested in recurrence analysis through a project I was working on that was focused on new businesses and teams of people that were working to create new businesses. And specifically, we were studying the pitches. This is a project with Sigal Barsay to the Wharton School. We were studying the dynamics of new business pitches. And so the basic gist of this setting is you have a group of 5 people or so who are delivering a pitch of a new business to a panel of 5 judges. And what we were studying here was how synchrony between the panel of presenters and the team and judges influences outcomes. And so some of the data that we collected electrodermal activity for the presenters as well as the judges, and we got some data that looked something like this. So the graph on the left just shows the average of team members' activation and of how excited or anxious they were. The average of their electrodermal activity over time, leading up to their pitch, and then during their pitch and afterwards. Or another way to visualize this is kind of thinking about the convergence in group members' electrodermal activity over time. And so I initially became interested in recurrence analysis when I graphed these data and thought to myself, I have absolutely no clue how I would analyze these data using the standard types of methodological approaches that we often use in studying groups and teams. Many of those approaches that are rooted in the general linear model, which this type of data may not be quite so amenable for that. And indeed, if we think about how we often study longitudinal data or think about dynamics and processes within groups, we often handle these types of data in a few different ways. One approach that we often take is just to aggregate those data. And so I would take all of those data points, those thousands and thousands of data points, and I would just take the average and look at the average activation of a group over time. Or maybe I would use an approach where I just disconnect the temporal structure of the data. And so I look at these observations nested within people, but they're not really connected in terms of how they're flowing over time. A third approach that we often take is to linearize those data. And so, if we go back and look at this complexity, there are lots of dips and drops and rises over the course of time. One thing that we do often, though, is just to simplify that, drawing a straight line in between the start and the end point, or an average through there, and kind of ignoring those dynamics that are happening, smoothing over those. Or, depending on what your area of study is, qualitative methods might be an acceptable route, and you might describe what's going on using prose and qualitative terms and observing the processes that are changing over time. All of these approaches, however, were falling short for us in trying to think about and assess synchrony over time, because the more fine-grained data on group dynamics that we've collected, you see just how incredibly dynamic groups are over the course of time, with lots of potentially very interesting patterns and lots of interesting dips and rises in these data. And so we came to recurrence analysis as a different way of thinking about and approaching studying group dynamics. And what I think is valuable is to think about recurrence analysis as an alternative analytical mindset to the approaches that you currently take in thinking about your data. Analytical mindsets are the ways, the lenses that we use in viewing our data, and those lenses influence theory development. Indeed, this is something you can see if you just look at the incredible rise of multi-level models, conceptual models, that to some degree are driven by the popularity and the ubiquity of multi-level modeling on the analytical side. Similarly, things like moderated mediation, which has become incredibly popular, and models, conceptual models that depict moderated mediation, which are largely facilitated by increasing use of those analytical models. Or if you study relationships in groups, the development of the actor-partner interdependence model or the social relations model, these ways of thinking about how people relate to one another at an analytical level also shape our theory. Our existing mindsets, those different ways that we tend to think about longitudinal and data in groups, however, can mask group dynamics. As you saw in each of those graphs, the approaches that we take currently largely reduce the complexity of dynamic data over time. And importantly, they ignore potential nonlinear dynamics in data over time. They presume a linear process of change over time. And so recurrence analysis offers an alternative mindset. It's a technique that has roots in a different literature, roots in the systems dynamics literature, which is variously referred to as complexity theory or chaos theory. And it's a mindset that has been applied to the study of groups in the past. For example, going back to Arrow et al. In 2000, thinking about and considering a model of groups as complex systems and trying to apply some of the techniques from the systems dynamics literature to the study of groups. Just to give you an idea of how recurrence analysis is being applied currently in studies of groups and teams. And we see this more so in the cognitive psychology literature currently than other places. But recurrence analysis has been used to study questions like how does team coordination differ in teams that have stable membership versus changing membership? And so recurrence analysis here is a way of thinking about and measuring the coordination patterns within groups and the nature of coordination within groups. In this Gorman et al. Study, they used data on conversation patterns captured as people were talking to one another on walkie-talkies. The second study, how does the structural organization of conversation relate to decision-making quality? And so here again, it's about the nature of the system between two entities in this case, and how that relates to some kind of an outcome, in this case decision-making quality. But here recurrence analysis, and specifically cross-recurrence analysis, is used to assess the nature of the system. And recurrence analysis, as we'll see, provides some parameters that we can use for thinking about what kind of a system is this. Third question, do team members become coupled during a performance episode? And how does this relate to processes and outcomes? And so here again, this speaks to this idea of coordination, and recurrence analysis provides some useful ways to think about and measure coordination or coupling between entities that are interacting with one another. So just a couple of the recent applications that have focused in particular on interpersonal dynamics within dyads and within teams. So let me give just a broad overview of recurrence analysis, staying at a very high level and at a conceptual level. This is a technique, as I mentioned, that emerged out of the systems dynamics literature. And systems dynamics historically was an area of inquiry that relied heavily upon graphs and depicting data and depicting systems over time. And so each of these graphs that you see on the screen currently represents a different kind of a system that has different properties. And these plots here are recurrence plots. And we'll see more of what a recurrence plot is in a moment. But as you can see, even just by looking at the recurrence plot, something different is going on in each of these systems. And systems dynamics historically used these kinds of depictions to learn and discover fascinating elements of how things were changing over time and how systems were shifting and changing over the course of time. Much like social network analysis, which also started out as a visual approach depicting networks, recurrence analysis over the years has evolved to incorporate quantification. And so we can apply different metrics to these graphs and assess and measure different properties of the graphs that help to illuminate what kind of a system each of these is and what's going on over the course of time in these systems. Even outside of the group dynamics literature, recurrence analysis has been used in many different disciplines, and it's a technique that's growing in popularity. It's been used in economics, in conversation dynamics, as I mentioned before, in medicine, and specifically in cardiology, as a way to understand what is it about a system that may make it special or unique. Here's a roadmap for, again, at a very high level, what you would do in conducting a recurrence analysis. The first step, obviously, is collecting time series data. And so this is a technique that focuses on dynamics, and to assess dynamics, we have to have data over the course of time, in this case in groups. And so we need to collect multiple observations of a group doing something over the course of time. A second step, and something I'll say more about in a moment, involves projecting this time series data, which we typically collect as a single dimension. We're going to project that into multidimensional phase space. And I'll say more about this in a moment, but phase space is a concept in physics to represent in a multidimensional way what the nature state of a system is at a given point in time. In the third step, we will use that phase space representation, and we're going to transform that into a recurrence plot, where we are plotting the system against itself over the course of time. And then in the fourth step, we're going to quantify the patterns within that recurrence plot using a few specific metrics. And so we're going to measure some of the attributes of the plot that we create in step 3. So let me go through each of these steps in a little bit more detail before we dive into actually looking at some code for how you would analyze time series data. A few notes just on this first step of collecting time series data. For most applications of recurrence analysis, you're going to need either fairly fine-grained data on groups, or you're going to need large-scale data on groups. And those are one and the same, but I'm separating them in thinking about how you might collect data. And so, for example, if you're collecting data in a laboratory setting and you have a group of people coming together for a 1-hour task or a 1-hour conversation with one another, you're likely going to need fairly fine-grained assessments of what's going on in that group within the 1-hour period of time. In contrast, if you are studying groups in the field or groups historically, you might collect data over many, many years on a single group. So, for example, we might imagine observing something about, let's say, a sports team that has been in operation for 100 years, and we could examine some of the properties of that over a very large scale of time. Recurrence analysis becomes especially useful when you have lots of observations. You certainly can use this technique and apply this technique to a small number of observations, but as you'll see in a moment, it becomes particularly useful when you have at least a few hundred observations, and becomes potentially very interesting when you have several thousand observations on groups. In the empirical illustration that I'll use with the code, we assessed group activation, which we measured using electrodermal activity, at a temporal resolution of 1 second. And so every single second we're assessing activation. And for groups that are working on a 30-minute task, that yields 1,800 observations per group. So let me speak about this second step, which is projecting the system into phase space. Phase space is a multi-dimensional space. We're going to think at a fairly abstract level here, at a conceptual level. It's a multi-dimensional space that a system is moving through over the course of time. And so in this graph on the right of the screen, we can think in 3 dimensions. And if we have a group that's moving through different states over time, we can think about that group moving through different places within this multi-dimensional space. Even if we only have collected data on a single dimension of that group, it has other components that we're not observing. And this is an important concept within the systems dynamics literature in thinking about where a system is. What is the state of a system at a given point in time? And we are going to think about that, especially when we're using continuous data, we're going to think about that as a multidimensional state. Now, the challenge of using phase space as a concept is that we usually only have one measurement of the many dimensions that might characterize a system. And so in the example that I'll show where we're measuring group activation, there are other elements that we are not observing, other components of activation that we're not observing. And so the challenge is that we have to somehow approximate, somehow we have to try to represent this system in an accurate way, even though we only have a single dimension of data. Fortunately, and now many years ago, Takins developed an approximation where we can use a technique called time-delayed embedding, where we are going to unfold the single dimension of data into multiple time-lagged dimensions. This is a bit beyond the focus of this presentation in particular. This is an important topic, however, and so I strongly recommend consulting additional resources as you are using recurrence analysis, especially if you have continuous data and you're using this time-delayed embedding approach. Because to use this, you have to make a few important decisions, one of which, how many dimensions do you need to appropriately represent a system in phase space? And it's common to use what's called the false nearest neighbor methodology to do this, to make this decision. Second key decision is what is the right time lag? And for this, there are common recommendations to use the mutual information function. But again, these are nuanced decisions, and it's important to read further about how you are embedding a system in phase space and what might the right decisions be given the nature of the data that you have. The third step, once we have done this process of time-delayed embedding, which is taken our single dimension time series data and made it a multi-dimensional data set, the next step then is to create a recurrence plot. Now, a recurrence plot is a two-dimensional plot that depicts when a system revisits a state that it has been in the past. And so if we take our phase space representation that's here on the left side in A, and if we visualize this as a recurrence plot, I'm going to highlight a few things. First of all, we're in two dimensions, and our two dimensions are time. So both the x-axis and the y-axis represent time. And because this is a single system against itself, you'll see immediately that this is a symmetric plot, meaning that what's going on in the upper triangle is the same as what's going on in the lower triangle. And furthermore, the center line is completely solid. The reason that's the case is that at any given point in time, a system is in the same state. And so if we go over to 60 and up to 60, the system is in the same spot. Now what we're doing in recurrence analysis then is saying, when else was a system in the same spot that it was at time 60? And it was also in the same spot around here at time 75. And so a recurrence plot is visualizing the times when a system revisits a particular state. Now let me use just a very simple example to illustrate what a recurrence plot is. And in this example, what I'd like you to imagine is a train that's running along a single directional track. And the train is just moving east to west and then back again over the course of the day, starting at 5 a.m., and it's going to do this throughout the day until 11 p.m. And it's stopping at 10 stations as it moves across the day. And so if we just look at our normal time series representation of these data, we see at 5 o'clock it's at station 1, at 6 o'clock it's at station 5, at 7 o'clock or so it's at station 10, and then it's going to come all the way back, and it's back at station 1 at 8 p.m. So it's just moving back and forth. If we represent this as a recurrence plot, this is what the visualization looks like. And so you see that it is at station 1 here at times 5, 8, 11, 14, 17, 20, and 23. And you see that reflected in the recurrence plot also. There's a dot for 5, 8, 11, etc. And so the recurrence plot is just marking when is that train at the same station throughout the day. Now this pattern that you see, we'll describe a bit more how to interpret things like this, but you see, again, it's symmetric. Upper and lower triangles are the same. You see that there is that solid line in the center, trains at the same point at 5 p.m., 6 p.m., 7 p.m., etc. But you also see lots of other diagonal lines. Now this is going to be reflective of a pretty deterministic system. We can predict how this train is moving throughout the day, and so we see these cycles of how it's revisiting prior states over the course of time. Now, there are a couple of complications in creating that recurrence plot. It's pretty easy to do if you have categorical data because a train is either at the station or it's not at that point in time. But due to phase space embedding with continuous data, we usually have multidimensional data, number one, and we also have this problem of what constitutes a recurrence. Now, how close to the station does the train have to be for us to call it at the station? And so in this visualization of phase space, if we imagine two states here, are these the same state? Does this constitute a recurrence? Or do they have to be even closer in space? And so that is a critical decision to make when you have continuous data of what constitutes a recurrence. Now for the multidimensional component, we can think in terms of distance, and we can calculate, for example, the Euclidean distance between the system state at 2 points in time. But we do have to choose that threshold value, some value that we say anything that's closer than this, that counts as a recurrence. Anything that's further away from this threshold, that's not going to count as a recurrence. One common recommendation, especially if you're focused on the structure of the system, is to set a threshold value such that between 2 and 5% of the points in the plot are classified as recurrences. Why that's important is if all of the dots in the plot are shaded, are all recurrences, there's no structure to analyze at all. At the other extreme, if nothing is classified as a recurrence, then again, there's no structure to analyze in that system. And so we want to generate some recurrences. We want to mark some things as recurrences so that we have the ability to understand elements of the system. The fourth component here is to quantify the pattern of recurrences. And so we're going to use that recurrence plot, and we're going to calculate a few different metrics. And there are many that you could calculate. I'm going to focus on just a handful of these. And these metrics are going to tell us something about the system. And here's where this becomes especially useful in thinking about and studying groups, is that we can start to understand a bit more about the coordination or the predictability of the dynamics within that group. And these are the ones that I'll go into a bit more detail on. So the first, the recurrence rate. This metric assesses how intensely a system visits the same states over time. And so this would be evident. You're going to have a high recurrence rate if many of the points are filled in the plot. Recurrence rate is directly measured as the proportion of points that are marked as recurrences divided by the total number of possible points that you could mark. If you're using discrete data, can be a particularly useful metric in understanding your system. With continuous data, though, you'll recall I mentioned a moment ago, we often set the recurrence rate, we fix it to between 2 and 5% of the plot. So that we can better understand and use some of these other metrics that follow. The second metric, determinism. Determinism assesses how much a system's dynamics are predictable, that is deterministic, determined by something. And determinism is evident in the presence of diagonal line structures. that are running parallel to the main diagonal. And so this is saying that a system is visiting the same sequence of states over time that it has visited at a prior point in time. Determinism is measured as the proportion of the points in the plot that form these diagonal lines. Now we have to identify then what constitutes a diagonal line. Are 2 points in a row enough, or do we need 3 or 4 points? A common default in many software packages is to use 2 points as the minimum number to constitute a diagonal line. Also focusing on these diagonal line structures, we can also think about how long are they? And so for a given plot, how long is the longest diagonal line structure? Which suggests if you have a very long diagonal line, that means the system is literally moving through the same pattern, the same sequence of states that it has moved through at a prior point in time. Maximum is one. The other thing we can think about is the average diagonal line length within the plot. And here, if we have longer diagonal lines in general, it suggests that this is a relatively more predictable system. It's a more determined system as the system is moving through certain states for a sustained period of time. And so again, if we think about that simple example of the train moving through time, you see these long diagonal line structures. These long diagonal line structures make sense because we know this system is determined. It's determined by a schedule, and the train is stopping at a different station in fixed patterns of time. And so we would expect there to be a deterministic pattern in the recurrence plot. The last metric that I'll describe, entropy. Entropy assesses how complex the deterministic structure of a system is. And in recurrence plots, this is typically measured as the Shannon entropy of the system. Systems that are high in entropy have very complex, very nuanced deterministic patterns that are characterized by a plot with diagonal line lengths that are of various lengths. And so when you have these diagonal lines, some are 2, some are 3, some are 4, some are 5, 6, 7 long, that suggests that there are several different deterministic patterns that are happening within this system over time. A system that's low in entropy, so it has a pretty simple deterministic structure, is going to be reflected by a fairly similar homogeneous pattern of diagonal line lengths. And so again, we can think about that simple train example where we've got fairly similar diagonal line lengths because it's a relatively simple structure of a system. It is driven and it depends upon this simple schedule. So let me illustrate walking through these different components. Now shifting and looking at some actual data and moving through the kinds of things that you might do if you were to conduct a recurrence analysis. And the data that I'll use for this stem from a study of groups working together in an experimental setting. And we have 54 groups here, 214 people. These are undergraduate participants, groups of 3 to 5 people, and they're working on a creative task. And so they're charged with developing an idea and then presenting their idea at the end of their working period. And these folks are going to work together for 30 minutes at a time with that performance component at the end. The focal variable that I'll use in this illustration is physiological activation or arousal, which is operationalized using electrodermal activity. And so each individual wore a sensor over the course of the study that monitored his or her electrodermal activity. And what I'll use in this illustration today is the group average of the individual activation samples that is marked at each second in time that these folks are working together with one another. So let me switch over to some code. And the specific piece of software that I will be using here is the open source and widely available platform R. And I'll use a couple of different packages that I'll highlight as we go forward. There are many different ways that you could use R. Some folks like to use it in an integrated development environment. What I'm doing here is I'm just using a text editor, Text Wrangler, and R console is over here on the left side. And so this is my code here, and this is where you'll see some of the output as we're going forward. So the first thing I'm going to do is just bring in some of the data. And let me just show you what this data set looks like. I'll show 15 observations out of this data set that has approximately 1,800 observations. And so, I'm sorry, 1,800 observations per group. And so what you see in the data set on the left side, there's a variable for the team, marking each team's data. Then there's a variable representing the second, ranging from 0 to 1799. And then there's our measurement of electrodermal activity, which I've standardized just for the quirks of electrodermal activity. It's nothing to do with recurrence analysis, but I've standardized the electrodermal activity here. So 3 variables in this data set, and there are 113,400 observations in this data set. So the first thing I'm going to do is I'm just going to plot one group's data first, just to give you a feel for what these data look like over the course of time. And so what you see here in this graph, the blue line, this just represents one group. So each point here would be the average of group members' electrodermal activity at that second in time, ranging from 0 to 1799. Electrodermal activity is along the y-axis. And so what you see is there is a relatively steady, slightly quadratic increase in electrodermal activity over the course of time in this group. But let me add a second group here. And so I'll add a second group's data in red, and you see a fairly different pattern over the course of time in electrodermal activity in our second group, in our red group. And so I'm going to focus the illustration on just these 2 groups for now, as we go through and we convert and use recurrence analysis to try to make sense of these different time series of data. The package that I'm using here, which is freely available, is the CRQA package by Moreno and Dale. It was last updated in 2015, I believe, and there is a tutorial paper that you can download that walks through in great detail how to use this package. So I'll just load that. And now what I'm going to do is I'm just going to store 2 groups' data. And so I'm going to create one time series 3, that just has the electrodermal data for group 3. And so all this is 1,800 values showing group 3's data. And I'm going to do the same thing for a second group, group number 40. Now, in using the CRQA package, which stands for Cross-Recurrence Quantification Analysis, it has several functions that are very useful for doing some of the steps that I just walked through at a conceptual level. The first of these is a function called optimize param, and this optimize param function helps you choose the number of dimensions, the delay, and the threshold that are needed in that phase space embedding process that I talked about, as well as in marking something as recurrent or not. Doing that requires setting some initial parameters, and I would encourage you to study the manual for cross-recurrence quantification analysis and thinking about what values might make sense for your particular data set. Here I'm using mostly the defaults. And so I'm going to do this optimize parameter function here. And what this is going to give me is for each of these groups. Again, we're working with two groups right now, group 3 and group 40. And so after running this, what you see on the left side is I've got a radius. That's that threshold value. I have a dimension and a delay. And so these three parameters are needed for doing the recurrence analysis using phase space embedding. And now I have those for each of these groups. And so the important thing you'll realize here is that each of your groups, which constitutes a separate system, each of your groups has its own parameters for phase space embedding. I'm just going to visualize the recurrence plots for these two groups before we do any quantification. And I'm going to use the sparse M package that will just, this is just for producing the image, just for giving us the graph, the recurrence plot itself. And so how I generate this recurrence plot is first I use the CRQA package, and in this single run for each of these groups, I will be getting information for the recurrence plot, and I'll also be getting the quantification indices that we'll look at in just a moment. So first, let me just run for each of these groups. And now, just to refresh our memory for what the groups looked like, here was group number 3 in blue, and here is group number 40 in red. And so now let me produce recurrence plots for each of these groups, just using the image function from sparse M. So here are the recurrence plots for these groups. So one thing you can see is first the plots look very different, and this is indeed what initially systems dynamics folks would look at, is the plot itself to make sense of the system that they're viewing. But look at how we have a steady increase in the blue group, and the recurrence plot, one thing to note is it's just flipped from what we'd seen before. So time is, it's running in this direction here, from upper left down to lower right. But you see clusters of recurrences here, and this corresponds to some of the activity here in this group. Then there's some bouncing around here, and then this sporadic activity here at the end, where the group is revisiting some prior states, but it's also clustered around a new space, and where it's moving through phase space. Now, if you contrast that to this red group over here, you see this red group is revisiting prior states at other points in time. And indeed, there's almost this separate trajectory here at a different point in time. And that corresponds in the graph, if you see this upward sloping part here, and you see this again in the red graph over here. And so this kind of upward movement and upward trajectory, we see some of this reflected in the recurrence plot. But of course, plots, especially if you have data on several groups, we need to quantify those plots. And so just in running the CRQA function up here, we've already generated the information for viewing the metrics. And so now I'm just viewing the results of what we've already done. And this is for group 3. I've chosen those same metrics that we saw before, and so I get an assessment of the recurrence rate, the determinism, which, as you recall, is about predictability in the system, the maximum diagonal line length other than the main diagonal, the average diagonal line length, and an index of entropy. And so we can do the same thing for group 40. And I'll just put these together so we can see them together. And so we see group 3, these are the recurrence metrics, and group 40, here are the recurrence metrics. Now this is obviously pretty cumbersome if we have 54 groups, which we do in this data set. And so we can easily in R loop through all of the teams in the data set, just doing that exact same process that we did before. And that's here represented in this section. I've just written a little loop to move through each of the groups, optimize the parameters for that particular group, get the recurrence parameters for that particular group, and I'm storing that information. This takes a little bit of time to go through 54 groups, and so I've already done that before we joined today. And this is what that output would look like. You see we have the same information as above, additional metrics that are available that the CRQA package provides. And now you see one row for each group. And each group has each of those recurrence quantification metrics. And now we could use this, merge this with a separate data set, perhaps to look at the relationship between determinism, perhaps, and outcomes for that group. How high quality was the group's final product, for example, or to survey ratings of coordination and cohesion or commitment in this group. And so we can now use these metrics in additional analyses as measures of attributes of the system over time. Now, one thing that's very clear is that these groups differ. And so here's just a histogram of entropy across these 54 groups. And we see it's a relatively normal distribution. We've got some variance here. And so groups differ in terms of how complex their deterministic structure is. And that might be particularly valuable and interesting in thinking about the group's coordination and the extent to which the group is delivering high-quality outputs. So here's one approach for doing recurrence analysis. As I mentioned, there are several others just within R. I've highlighted some of the other packages that also provide recurrence analyses and recurrence plots. T-series chaos, nonlinear T-series, and F nonlinear, all will generate some components of recurrence analysis. I tend to prefer the CRQA package. It offers a little bit more flexibility than some of these other ones. So there are a few other options for analyzing data and doing a recurrence analysis. And one thing I'll highlight is this is an incredibly dynamic area with lots of innovation happening right now. And so I would encourage you for regular updates on what's the latest and greatest in analyzing your data. First of all, there's a very useful Twitter feed just called Recurrence Plot that provides regular updates as well as examples of articles that use recurrence analysis. And this website, recurrence-plot.tk, is probably the best resource on the web for recurrence analysis. There's an entire page that lists software applications that will help you conduct recurrence analysis. Some of the current options that are listed there, there's a MATLAB toolbox if you use MATLAB that's very helpful. There's an older command line script that's also very good for doing recurrence analysis and that would apply across platforms. And finally, as I mentioned, several packages in R have recurrence analysis functionality. So let me wrap just by highlighting two particular extensions or variations of recurrence analysis that are becoming more popular in research on interpersonal dynamics. And the first is a windowed recurrence analysis. And so what this does is subsets or divides each group's time series into a series of windows. And so for our 30-minute task in that last exemplar application, we would be viewing in smaller slices, maybe 5 or 6 minute slices over the 30-minute window. We would be zooming in and studying the dynamics within that window. And so we'd conduct a recurrence analysis on those subsets of the data. And this would help us understand how the nature, the properties of a system might be shifting over the course of time. CRQA does have functionality for doing a windowed analysis. There are a couple of useful functions for doing that. The second variation of recurrence analysis that I'll mention is cross-recurrence analysis. And this examines how two systems relate to one another. And so imagine if we had just a dyad, two people working together. We could conduct a recurrence analysis using those two individuals as separate time series data sets. And this approach is particularly helpful for studying synchrony between two entities or two systems. And again, CRQA does have functionality for doing that directly within R. This is obviously a complex topic, but it also has some incredible extensions that way beyond what we have time to go through today. And so I'll just highlight a few resources that are especially useful. First, before doing a recurrence analysis, do read this paper by Marwan et al., which is an incredibly helpful introduction as well as very detailed treatment of recurrence analysis, as well as a follow-up piece, always helpful, which is how to avoid pitfalls in recurrence analysis, also by Marwan. And there are a few other useful things that you might find on the web. Weber and Marwan have a book, an edited book, which actually you can download the PDF of this book online. It focuses on recurrence quantification analysis. And there's an older chapter by Weber and Zbillet that is very helpful in walking through some of these different steps. So let me stop here and take any specific questions that you have or places where you'd like me to go back in greater detail.
One question that I have is that will come through is, so I do group feedback research, and so there's a lot of interconnections in terms of how feedback is provided among members, and then the idea is that leaders will use that feedback to enhance the group process or make changes to the group process with the group members to improve outcomes. And I'm curious if you think recurrence analysis would be a good fit for that type of data in group psychotherapy research.
Mm-hmm. So I think it could be. It could be, especially, one way to use this analytical approach is in an experimental design. Let's imagine that you have two conditions, different ways or approaches that people are using in providing feedback, and you could study the impact of that on the conversation dynamics between the two individuals. One extension that I didn't get into here, but you can use recurrence analysis to understand who's leading or lagging in a dyad. And so for cross-recurrence analysis, you could use this technique to understand who's following whom in a conversation. And it strikes me that that could be something particularly useful for thinking about the provision of feedback.
Wonderful, thank you. Looks like the only question that's come through, but thank you so much for providing some of these resources where we can follow up. Would it also be available for members who are attending or those who have recorded or watched the recording to be able to contact you with further questions?
Sure, absolutely.
Perfect, thank you. All right, well, thank you so much, Dr. Knight, for your presentation today. It's been incredibly helpful and informative, and hopefully others are taking quite a bit away from this like I am. If anybody has any final questions, we can take them now, or we will end up for today.
Okay, great.
All right. Thank you so much, Dr. Knight. I really appreciate your time.
Thank you.